last time I just started talking about conditional probability. Let me write again the formula that was the last to be written last time. It's this. Okay, now this is the formula for conditional probability. Now officially in full, it's read this way. The probability of event A given that event B occurs. In short, it's read P of A given B. And this is the formula to compute the conditional, used to compute the conditional probability. Now, last time we derived this formula on the basis of the classical probabilistic model. And within that model, this formula is just a matter of simple arithmetic. It can be easily obtained. But the application of this formula is not limited to the classical model. Outside this model, this formula is accepted as the definition of conditional probability. And it works for any probabilities of any origin. All right. Now, the right-hand side here is a quotient. The numerator is the probability of the joint event, A intersect B, and the denominator is the probability of event B. And because we have this denominator here, we need to stipulate that probability of B should not be equal to 0. Okay, let's give it a simple example. It will be about horse race. Okay. Well, the classical model can hardly be applied to any events that are related to horse race. It's a matter of judgment. Okay, there are lots of experts that understand a lot about this, know a lot about horse races, or at least they think or are believed to know a lot. Suppose we have this expert opinions. Expert number 1 says that the horse named Hurricane and the horse named Thunderbolt will be the first two to come in with probability 0.8. So Hurricane and Thunderbolt will be the first two to come in with probability 0.8. And we have another expert opinion. Expert number 2 says that Thunderbolt will come in first with probability 0.2. Thunderbolt will come in first with probability 0.2. Okay, so no classical model here, just expert opinions. Now let's assume that both these expert opinions make sense. Basing on these, what is the conditional probability that Thunderbolt will come in first, given that this prediction is also true? So what's the probability? Let's write it here. Probability Thunderbolt first, given that Thunderbolt and Hurricane are the first two in some order. Okay, and we are going to use that formula. what is the numerator here? The numerator is the intersection of the two events. The numerator here is the probability that both these events occur. But if we look closely, we will notice that the intersection of these two is just the same as this one event. Okay? In terms of sets, it means that this set is a subset of this larger set. So the intersection of the two is identical with the smaller set here. So the numerator is T first, and the denominator is the probability that thunderbolt and hurricane are the first two. Okay? And we have exactly these probabilities. We have focused of these probabilities, and it's 0.2 divided by 0.8, which is this. So if these focus make sense, if they can be relied on, then the conditional probability of thunderbolt coming in first, given that thunderbolt and hurricane are the first two to come in, must be this. Okay? I give you this example specifically to illustrate that this definition of conditional probability can be applied outside the classical model. Okay? Well, next. We obtain something very important if we multiply each side of this equation by the denominator here, by the probability of B. The result can be written in this way. Probability of A intersect B equals probability of A given B times the probability of B. And this is a very important formula. It's called product law. Now, it's the formula that allows us to compute the probability of the intersection of two given events. Now, please notice that the right-hand side here contains the conditional probability, P of A given B. Let's give it an example. Now, 20% of the applicants that come at some university, so 20% get admitted. Some 20%, I'm sorry, let me write it in greater detail. 20% of all the applicants get admitted. Okay, and then 85% of those admitted finally graduate from this university. 85% graduate. Now suppose we choose one applicant at random. What's the probability that he or she will eventually graduate from this university? Now, again, we can interpret this as the joint event, be admitted and graduate. And be admitted. Okay? Well, it's not very well written, I'm afraid. I'm not famous for good handwriting, you know that. But in case somebody can't read it, it's the probability of graduating and being admitted. But because you cannot graduate unless you are admitted, it's the same as just graduating, okay? But because we write it this way, we can use this formula now, the formula for the intersection of two events. And we write it this way. the probability of graduating given that you're admitted, which is given as 85%, okay, and it must be multiplied by the probability of being admitted, which is 0.2, and this is what we get as a result. So if we select at random one applicant to this university, the probability that he or she will finally graduate from it is this. All right. This product law can be extended to problems involving more than two events. Well, suppose we have three events, A, B, and C. How do we compute the probability of the joint event, A intersect B intersect C? Okay. Now, if we use a Venn diagram here, what are we talking about here? Suppose this is A, and this is B, and this is, okay, not a circle, and this is C. Now, this shaded area in the middle is the intersection of all the three events. Okay, using this formula once, we can write it this way. Probability of A given B intersects C times the probability of B intersects C. Okay? Do you notice that I use B intersects C as a condition here? Okay. Now, if I look at this term separately, I can apply this formula again, which gives me this. Okay. So probability of A given both B and C times the probability of B given C times the probability of C. Now let's give it a simple example. Well, suppose the Weather Bureau says that the probability of tomorrow being a dry day is 0.5. Tomorrow dry is this. Also, the same bureau says that if tomorrow is dry, then the day after tomorrow will also be dry with probability 0.4. So, day after tomorrow dry, okay, given that tomorrow is dry, is cited as 0.4. Okay, again, a not very well written phrase. So the probability that the day after tomorrow will be dry, given that tomorrow is dry, is estimated to be 0.4. And also, and the same bureau says that the probability that the next day, well, let's call it the third day. We have tomorrow, day after tomorrow, and the next day, let's call it the third day. So the third day will be dry, given that the first two are dry, first two are dry, it's estimated to be 0.3. Now, if these estimates are reasonable, if they can be relied on, what's the probability that all the three days will be dry? Tomorrow, day after tomorrow, and the next one. using this formula, we first write the probability that tomorrow will be dry, which is 0.5. Then we multiply it by the probability that the day after tomorrow will be dry, given that tomorrow is dry, which is 0.4. And then we write this, the probability that the third day is dry, given that the first two are dry. And this is 0.3. Okay, and what is this probability? I think it's, is that correct? Well, I think yes, it is. So it's my mental computation. All right, which is not very good. So this is how we use this formula in the case of 3 events, and you can easily see that this can be extended to any number of events. Okay, so if we have 4 or 5 events, we can always develop a formula for the intersection. All right. Next, the next big thing to discuss is independence of events. Independence. Now, we have just talked about conditional probabilities. We know by now what the conditional probability of any event given any other event should mean. Now, considering this, what do we mean by saying that this or that event is independent of some other event? Now, the natural thing to say is that we talk about independence if the conditional probability is the same as unconditional probability. Okay? And suppose we have 2 events A and B. The conditional probability of A given B is, well, is this, and if it's the same as just A, a probability of A, then we say that events A and B are independent. Okay? Now, what do we get if we substitute the right formula for this? Probability of A intersect B divided by the probability of B must be equal to the probability of A. And this can be used as the definition of independence. So two events are independent, or rather, let's put it this way. If 2 events are independent, then we expect that this is true. But there is a complication. This formula requires that the probability of B be not 0. Okay, this is a restriction. And we get a more general formula if we multiply each side by the probability of B, and then we get this. Okay. Well, these two formulas are almost equivalent, but this one doesn't work if the probability of B is 0, and this one can be applied to any events, including events that have 0 probability. Now, this is accepted as the definition of independence. So now, 2 events are called independent if this formula is true. Okay. Now, you may notice that if at least one of the 2 events is a null event, and accordingly its probability is 0, then using this definition, 2 events are independent if at least one of them is a null event, which is a consequence of this formula. All right. Let's give it some simple examples. Okay. drawing a card. Drawing a card at random from the standard 52 card deck. Now, what's the probability of getting a heart? This is a classical model, of course. What's the probability of getting a heart? Hearts are one of the four suits in the deck. There are 13 hearts in the deck, and there are 52 cards in total, so the probability is 1/4. And each, actually, this is the probability associated with each of the four suits. And what's the probability of getting a king? How many kings are there in the deck? 4, okay? So 4 is divided by 52, and the answer is 1/13. Question, are these two events independent or not? Well, it's natural to expect that they are independent because we have this very symmetric situation, 4 suits, equal number of cards in each, and so on. And yes, if we apply this definition, let's first try to apply this one. Now, what's the probability that a randomly chosen card is a king given that it's a heart? Given that it's a heart. Now let's go by the definition. What's this conditional probability? It's the probability that it's a king and a heart divided by the probability of a heart. Now, there is one card like this. It's the king of hearts, obviously. So it's the numerator here is 1/52. Okay? And it must be divided by the probability of a heart, which is this. And after some simplification, this is what we get. This is the conditional probability of getting a king given that it's a heart using the formula for conditional probability. And what's important for us here, it's just the same value as this one. So the conditional probability of getting a king, if it's a heart, is equal to the unconditional probability of getting a king of any suit. Okay? So these two events are independent, this and this. Well, we will arrive at the same conclusion if we look at the probability of it being a card, a king and a heart. It's just the same thing, just a slightly different approach. Now, it's just, well, we can compute it independently. There is only one card like this, and there are 52 cards in total. And the question now is whether this probability is equal to the product of the two respective probabilities, probability of getting a king and probability of getting a heart. Is it a correct arithmetic statement or not? Well, yes, it is. And this is another way to establish that these two events are independent. Okay? Well, this is a very simple example. Let's discuss another one. Okay. Example. Suppose there is a certain important international organization that has that has 32 offices. 32 offices. And well, a lot of those offices are actually spies. They are spying for some country or other. Well, I invented this example. I really hope there are no organizations like this, but to keep you amused, I think it's going to be fun. So of these 32 offices, 10 officers spy for the CIA only. 10 spy for the CIA only. Okay, and 6 spy for the FSB only. For the FSB only. Well, and also there are 6 double spies, 6 officers that spy for both intelligence agencies. So 6 spy for CIA and FSB. Now suppose we select one officer at random out of this total number of 32. The event, one of the events is this. This randomly chosen officer spies for the FSB. And we have this other event, a randomly chosen officer spies for the CIA. Question, are these two events independent or not? I must say that my intuition is not enough to answer this question just by looking at these numbers. And by the way, this is typical of probability theory. Quite often our intuition is not sufficient to answer even simple questions. And this is the power of probability theory. It allows us to get answers to tricky questions. This seems to be a very simple situation, but actually I don't answer this simple question without actually applying the formula and doing computations. Now let's apply the formula. Well, what's the probability that a randomly chosen officer is an FSB spy? FSB spy. Okay, we need to divide by the total number of FSB spies by the total number of officers. And how many officers are FSB spies? It's this plus this. Okay, so it's 6 plus 6 divided by 32. And after simplification, we get this answer, 3/8. And what's the probability that this randomly chosen guy is an CIA spy? The total number of CIA spies is 10 plus 6. 10 plus 6 over 32, and this simplifies to 1/2. Okay? Okay, now let's ask this question. What's the probability that this randomly chosen officer spies for the FSB, given that he or she spies for the CIA? Conditional probability. FSB given CIA. What's this conditional probability? We apply the formula. Now the numerator is the probability that this person spies for both agencies, and is computed by dividing the number of members in this intersection, which is 6 divided by 32. 6 divided by 32, and then and the denominator is the probability that this is a CIA spy, and this is known to be 1/2. Okay, and this simplifies to 3/8, which, look at this, which is the same as the probability of selecting an FSB spy unconditionally. Okay, so these two events are independent. And of course, you can arrive at the same conclusion if you consider the probability of, if you divide 6 by 32 and compare it with the product of the two respective probabilities. What I wanted to illustrate by this example is this. Actually, the concept of independence in probability theory is not very simple. It's rather tricky, and it's not very intuitive. So again, my intuition is not enough to arrive at the right conclusion just by looking at these figures. And what's more, actually, I chose these figures specifically to make these two events independent. If you add one officer spy or not, if you add one officer to this total number, these two events will no longer be independent. You can check that this is true at home. It's even less simple if we talk about 3 or a greater number of events. Let's look at 3 events, and let's try to understand what independence means in the case of 3 events. Let's call them A, B, and C. What should we understand by the independence of 3 events? Well, of course, we expect that the probability of A intersect B is the product, I'm sorry. We expect that this kind of equation is true for any pair. For each pair, A intersects C equals P of A times P of C, and P of B intersects C equals P of B, B of C. Is that it? Is that all there is to it? Now, the answer is no. Yes, we need to require that these 3 equations are satisfied if we want these 3 events to be independent. But it's not enough. We need to require something else. We need to require that A intersection B intersection C be equal to the product of the 3 respective probabilities. And mind you that this is not a consequence of the first 3 equations. Let's give it an illustration. Suppose we select one element at random from this sample space. 1, 2, 3, 4. So we choose one number at random out of this set. Let's define event A that the number chosen is 1 or 2, and B is defined to be the event that it's 2 or 3, and C is the event that it's 1 or 3. What are the probabilities? Probability of A equals 1/2, and this is also 1/2, and this is also 1/2. What about the intersections here? The probability of A intersect B. Now, what is this set, A intersect B? How many elements does it contain? Just one. It's just number 2. So it's 1 out of 4, which is equal to the product of the 2 respective probabilities, 1/2 times 1/2. Okay? And the same, we get the same answer if we look at the 2 other pairs. It's also 1/2, and the probability of A intersect C is also 1/2. So we have have discovered that these 3 equations are satisfied. But what about this 4th one? Now, what is the intersection of all the 3 events here? A intersect B intersect C. How many elements does it contain? Look at this. I want you to notice that it's empty. There is no number that is contained in each of these 3 events. So of these 3 sets. So it's a null event, and accordingly, well, this is a null event, and accordingly, its probability is 0. Is it equal to the product of the 3 respective probabilities? No. The product is 1/2 times 1/2 times 1/2, which is 1/8, not equal to 0. So in this case, it's not enough to require that this kind of equation be satisfied for each pair, each of the 3 pairs. We need to require these two, and it's not satisfied here. Let's try to illustrate this situation using a Venn diagram. Okay, look at this. This is very approximately what's going on here. The intersection of any two of the events is not empty. And actually, it's such that the events are independent, any two. But not all the three of them, because the intersection of all the three is just empty, and the probability is 0. Okay? So, independence is not a very simple concept. Also, it's a very typical mistake when mutually exclusive events are believed to be independent, which is not true. So mutually exclusive is not the same as independent. Okay? Please write this down and pay attention to this. It's a very typical mistake. Again, let's illustrate it by a Venn diagram. Well, these are two mutually exclusive events. They have no points in common. Question, are they independent or not? No. The answer is no. They are not independent. How are they dependent? Now, if you think of it, they are not only dependent, actually it's an extreme case of dependence. If one of them occurs, the other one cannot occur. The other one is excluded, which is definitely not independence. It's a very strong case of dependence, an extreme case of dependence. So please do not confuse these two concepts. Okay. Next. Now, suppose we have a number suppose a certain number of events, E sub 1, E sub 2, up to E sub k are independent. Then it can be proved, but I'm not going to discuss a proof here, but just trust me. It can be proved then that the complementary events are also independent. Then and we agreed last time to use this notation for complementary events. This horizontal bar put over the letter means complementary event. And I'm telling you that the complementary events are also independent in that case. All right, now which means that the probability that all of them occur at the same time, intersection of all of them, 1, 2, okay, 1, 2, up to k. Well, because they are independent, can be computed as the product of the respective probabilities. 1 complement p of E2 complement probability k complement. Well, how is this formula important? There is a very important application to this formula. suppose we want to compute the probability that at least one of these events, E1 to EK, occurs. E1 or E2 or EK. Now let's ask ourselves, what is the complement of this event written here? What is the complement to at least one of them occurring? The complement is that none of them occurs. Do you get this? The complement to this is what's written here. So, because these two are complements, we can compute it this way. Okay? And substituting this expression, we get this final formula. 1 minus okay. Well, please enclose it in a box to emphasize it's important. A not very straight box, but okay. You make it better. You make it better. Do a better job of it. All right. Let me give you an illustration of how this formula is applied. Suppose we have a device that consists of 4 units. And unit 1 fails within 1 year of exploitation, fails with probability, with this probability, 0.01. Unit 2 fails with probability 0.2. Unit 3 fails with probability 0.3, and unit 4 fails with probability 0.4. Now let's assume that each of these units is critical for the operation of the entire device. If at least one of them fails, the whole device is out of operation. The question is this: what's the probability that the whole device will not fail within 1 year? What's the probability? Okay, it's not important. We can ask the question: what's the probability that it will not fail, or that it will fail? Let's say that probability that device fails. Okay, suppose we asked it this way: suppose the probability that the device will fail within 1 year of exploitation. I just wanted to match this formula. Then it's 1 minus the probability that the device does not fail, okay, which is 1 minus, and then we multiply the respective probabilities that each of these units does not fail. Probability that unit 1 does not fail, unit 1 does not fail, probability that unit 2 does not fail. Okay, like this, okay. And okay, let me continue here. Probability that unit 3 does not fail, and probability that unit 4 does not fail. Okay. Well, how do we compute all this? Do we have enough information to complete this work? What's the probability that unit 1 does not fail within 1 year of exploitation. Because it fails with probability 0.01, then it does not fail with probability 0.99. And here it must be multiplied by the probability for this second unit and this 8897 and 0.96. So again, this is the probability that the first unit does not fail, the probability that the second unit does not fail, and multiplying them together, we get the probability that the whole device does not fail, and subtracting the result from 1, we get an answer to this question, that the device does fail. And it's going to be this. Well, of course, it's a very simple example, but let me tell you that this formula and this approach are actually used in designing complex engineering systems and estimating the reliability of complex systems. It's a very useful and productive formula. All right. Okay, next. Suppose we have a partition. What is a partition? Now, we say that we have a partition of the sample space if the sample space omega can be presented as the union of a certain number of events, like this, such that each two of them are mutually exclusive. So omega is the union of a certain number of events such that the intersection of any two of them is a null event. Now, if we try to illustrate it by a diagram, now this is omega, and this is an illustration of how omega can be split into the union of a certain number of mutually exclusive events. Say, suppose this is A1, this is A2, A3, AK. Okay. Like this. Each pair is mutually exclusive, and put together they make up omega. All right. Now, suppose we have a partition like this, and also suppose we're interested in some other event, not one of these. Let's call it B. Well, it can be anywhere in this rectangle, okay? Now, suppose this is a representation of B, event B. Now, well, any event B that we may be interested in consists of these pieces that are the intersections of B with the respective events A. This is B intersect A1, this is B intersect A2, and so on. So these sections are mutually exclusive because A1, A2, and so on are all mutually exclusive. And these sections put together form B. Let's write it down. It's important. So B, if we have a partition, then we can write B intersect A1, union B intersect A2, up to B intersect the last one of them, and then each two of these are mutually exclusive. So B intersect AI intersect B intersect IJ is a null event. Well, this formula may look a bit too involved, but the meaning is quite simple. If we have a partition, then any event B that we may consider in this sample space is also subject to this partition. It also falls into a number of mutually exclusive sections. Okay. Now, how do we use this observation? Do you have a question?
Can you repeat the last order, please?
First, okay. First, let's again repeat the idea, the essence. If we have a partition, then any event B that we may consider also falls into a number of mutually exclusive parts. This is B intersect A1. This is B intersect A2, and so on. They are all mutually exclusive, and put together they form B. And this is exactly what's written here. B can be presented as B intersect 1 union B intersect 2, and so on. This is formula number 1 here. And this one tells us that the intersection of any two of these pieces is null. Okay? Well, how do we use this observation? It's just some preliminary work. Now, what the formula that we are actually going to use is this. It's called total probability formula. Well, because all these pieces are mutually exclusive, we can compute the probability of B as the sum of the probabilities of these intersections, B intersect AI. Okay? Well, again, I emphasize that here I use the fact that all these pieces are mutually exclusive. And also, I can express the probability of each such intersection using the product rule. So it's going to be P of B given A1 times the probability of A1 plus P of B given A2 times the probability of A2, and so on up to this B times this last, the last of the sets A times the probability of AK. Okay, so this is the formula of total probability, and quite often it's quite useful. Well, let's give it an illustration. Well, a certain student has 3 aunts. Aunt Lucy, Aunt Mary, and Aunt Sally. Well, and these loving aunts send these students letters from time to time. And what's more, some of these letters contain banknotes. Okay, this is the interesting part. Now, Aunt Lucy sends 2 letters a year. 2 letters per year, and each of her letters contains a banknote. So there is money in each letter from Aunt Lucy. Well, Aunt Mary, Mary writes 3 letters per year on the average, 3 letters per year, and letters from Aunt Mary contain some money 50% of the time. 50% of the time. Money. And Aunt Sally sends 4 letters a year. And her letters contain some money 20% of the time. 20% of the time. Okay? Is this setting clear? Is it a familiar situation or not? Well, suppose this lucky student who has 3 loving aunts receives a letter which is not signed, no return address. So it's impossible to understand from the look of the envelope which of the who of the 3 aunts sent it. Well, given this information, what's the probability that the letter does contain some money? And here we use the total probability formula. So, the probability that this unsigned letter contains some money can be computed using, now, what is the partition here? The partition consists of 3 events. The letter comes from Aunt Lucy, the letter comes from Aunt Mary, and the letter comes from Aunt Sally. Obviously mutually exclusive, and together they form the sample space. All right, so probability of money given that the letter comes from Aunt Lucy times the probability that the letter comes from Aunt Lucy plus probability that there is money in the letter given that the letter comes from Aunt Mary times the probability of Mary plus probability of money given Sally times the probability of Aunt Sally. Okay, do we know all that we need to know to use this formula? Actually, yes. Look at this first term here. What's the conditional probability that there is some money in the letter if it comes from Aunt Lucy? Where do we find it here? Money in each. So the probability is 1. And what's the probability that it comes from Lucy? It's a good question. Aunt Lucy sends 2 letters a year. And how many letters do all the 3 aunts send a year in total? It's 2 plus 3 plus 4, which is 9. So the probability that this particular letter comes from Aunt Lucy is 2 over 9. This first term is 1 times 2 over 9. For this other aunt, the conditional probability is 0.5 because only 50% of these letters, of letters from Aunt Mary contain some money. And what's the probability that this particular letter comes from Aunt Mary? It's 3 over 9. So it's 0.5, 3 over 9 plus. And for the last one, the conditional probability is, this one is supposed to be 20, okay? It's 0.2 and 4 letters out of 9 come from Aunt Sally, okay? Using the calculator, this is what we get, 0.478, okay? A very useful formula. Again, if you ask me, I must admit that my intuition is not developed enough to produce any reasonable estimate of this just by looking at these figures. I need to use the right formula, okay? Any questions about the total probability formula here? So this is the probability that you get some money if you get an unsigned envelope. All right. Maybe even more important is this. The total probability formula can be further to produce the famous Bayes formula, which is really, really important. Now, some comments on this name here. Well, first, nobody really knows the right way to pronounce it. I consulted the internet and found at least 3 different versions of pronunciation. Bayes, one of the versions. Bayes is another one, and some other versions are also possible. Now, actually, it's the name of a certain English mathematician who was also a priest, a clergyman. And it's interesting to know that he studied probabilities as a secondary kind of work for his major work, which was in theology. And he developed this formula that bears his name in the attempt to prove the existence of God, no less. Unfortunately, I can't tell you whether he was successful in that bigger stuff. I just don't know. I didn't find any information on that. But it's curious to know that sometimes people use probabilities to try to answer very big questions, really important questions, as in this case. Well, so far as I can guess, the existence of God has not been proved definitely after all. But the byproduct of this activity was this wonderful formula that is really productive and important. All right, let's say that we still have this partition. So the sample space sigma is presented as the union of a certain number of events that we call conditions here. We can call them conditions. Okay? And any 2 of them are mutually exclusive. So the same setting as for the total probability formula. I want to reproduce this picture here. So these are the conditions, A1, A2, and so on. And this is event B. Now, we can ask this question. Suppose now that B has occurred. Suppose now that B occurs. What's the probability that it occurs in combination with A1? We can interpret it as the conditional probability of A1 given B. Do you understand the question? It's kind of tricky, again, but it's important and productive. So what's the probability that A1 occurs given that B occurs? Okay? Because it's a conditional probability, we can use the formula A1 given B, A1 intersect B divided by probability of B. Also, we can apply the product rule in the numerator and the total probability formula in the denominator, which gives us this probability of B given A1, probability of A1, probability of B given A1, P of A1 plus probability of B given A2, A2 plus AK, B given AK, probability of AK. Okay, it's kind of long, but please be patient and copy it in your notebooks because you're going to use it a lot. All right, now let's look at this again. The numerator, which is the probability of a certain intersection, is written in this way using the product rule. Okay, and for B, we use the total probability formula that we just discussed. We present P of B as the sum of these partial probabilities. Okay? All right. It looks rather long, it looks rather awkward, but it's really powerful. Let's give it a couple of examples. Let's refer again to the example of a student and three loving aunts. So it's refer to previous example. Well, suppose the student finally opens the letter and finds a banknote, but no message at all. Because it's a habit with his aunts that whenever they send a banknote, they don't find it necessary to add any message, because money is message in itself, okay? This is the idea. So the student finds a banknote and no message, but the question arises, who of the three aunts actually sent this banknote? And let's try to compute this probability using the Bayes rule. Again, the partition is the same. It's either Aunt Lucy or Aunt Mary or Aunt Sally. But now we assume, we condition it with the event that the letter does contain money. So let's compute this probability. Suppose we're specifically interested in whether it's Aunt Sally or not, but the computation is perfectly similar for the other two aunts. What's the probability that the letter comes from Aunt Sally if it contains money? Okay, now we use this formula here. The numerator, probability that it contains money, given that it comes from Sally, times the probability of Sally. Okay, and the denominator is the probability that a letter contains money. And if we hadn't done this computation before, we would have to use this total probability formula. But we just did it in the previous example. So it's the total probability that an unsigned letter contains money. So we just know the answer, and we are going to substitute a numerical value here. Now, what is this? Substituting the numbers. 20% of all letters from Aunt Sally contain money. So the conditional probability of a letter containing money, given that it comes from Sally, is 1/5, and we multiply it by the probability that a randomly chosen letter comes from Aunt Sally, and it's 4/9. And here again, normally we would have to use the total probability formula, but let's not do it again because we just did it. We substitute this ready value, okay? And this is what we get, okay? And again, my intuition is absolutely helpless. I don't looking at just these numbers, I don't have any idea of what kind of probability this must be associated with. Okay, let's ask a different question here. What's the probability that the letter comes from Sally if it does not contain money? It's also a possible question here. So what is the probability that the letter comes from Sally if it contains no money in it? How do we change this formula here? We need to substitute the conditional probability that the letter contains no money, given that it comes from Sally. The conditional probability that it contains money, if it's a letter from Sally, is 1/5. So for no money, it's 4/5. And the same probability here, 4/9, which is the probability that the letter comes from Sally. And how do we change the denominator? We need to substitute the total probability that there is no money in the letter, which is 1 minus minus this, okay? Again, if we didn't have this ready-made value, we would have to compute this probability as the total probability. And performing this computation, this is what we get, 0.681. What I want to emphasize here, that these two probabilities do not add up to 1. They are not complementary events. It's easy to confuse these two with complementary events. They are not. If you think of it, it's a different question that is asked here. Okay. Any questions here? It's Bayes' rule. It's a very, very important thing. All right. Because it's so very important, let's give it another example, which is again, which is of considerable practical importance, by the way. And this other example is about testing in medicine. Suppose there is a certain serious disease, and in a population, 2% of all the members suffer from this disease. So 2% of the population suffer from a certain disease. But the disease is of the kind that may develop for a considerable length of time in latent form, unknown to the bearer of the disease, to the sick person. And this is a serious and dangerous situation. Well, 2% of the population are known to have this disease, even unaware of it themselves. Now, suppose the medical science has a test for detecting this disease. Test. Now, we need to know how reliable the test is, okay? And its degree of reliability is given by these two numbers. First, if the person that undergoes the test actually has the disease, then there is a 97% chance that the test will give a positive result. Positive means that the test indicates the presence of the disease, okay? So, if there is the disease, then 97% chance of positive result, positive test, okay? Well, I don't know what you think of this, but at first glance it seems good enough, reliable enough. On the other hand, there is this unpleasant other side to it. Any test, or practically any test, is capable of giving false positive results. So if a person does not have the disease in question, there is a possibility, there is a chance that the test will still indicate its presence. Okay, it's called false positive. Let's assume that if there is no disease, there is a 4% chance of a false positive result. Okay. Well, any questions about these figures? In the total population, 2% of all the members suffer from this disease, not being aware of it, without any symptoms. We have a test that allows us to detect the presence of this disease to some degree of certainty, to some degree of reliability. If a person has this disease, then we have this 97% chance that the test will give a positive result, but there is also a possibility of a false positive result. Now the question is this: suppose somebody, an individual, is given this test and the result is positive. Positive doesn't mean good, again. Positive means that the test indicates the presence of this disease. What's the probability that the disease is actually there? What's the probability that the person actually suffers from this disease? So what's the probability of, let's use this letter D for the event that the person has the disease. Given TP, and TP stands for the test positive, okay? And here we use the Bayes rule. Probability of test positive given disease times the probability of disease. And the denominator is the probability of test positive given disease times probability of disease, test positive given no disease times the probability of no disease. So again, I use some notations here just for shorthand. D stands for disease. The person who is given the test actually has the disease. And test positive, obviously, the event that the test indicates the presence of the disease. And pay attention at this, D with a bar over it indicates the complementary event, which is the absence of disease, okay? Now, what is the partition here? The partition is either this person has the disease or he or she doesn't, okay? This is the partition. All right. Let's try to plug in the numbers and actually get an answer. Now, what's this probability here? Probability of a positive test given the presence of the disease. We find it here, okay? So it's 0.97, and we multiply it by the probability that this person actually has the disease. And it's this. 2% of the total population have the disease. So we multiply it by 0.02. And the denominator is, we repeat the same term, and then we add this other term. What's the probability that we get a positive test given that there is no disease? And we look here. Okay. So it's 0.04 multiplied by the probability that the individual doesn't have the disease, which is the opposite of this. Okay, look at these numbers here. Any questions about how we use them? Okay, now and using the calculator. Now let me ask you, what is your guess? Considering this degree of reliability of the test, reliability is expressed in these values here. Suppose an individual gets a positive test. What's the probability that he or she actually has the disease? What is your guess? Well, I must admit that I'm helpless. I don't have any idea. Whether it's 0.9 or whether it's 0.6, I don't know. The actual answer is, well, to me, it's quite surprising. When I first learned about this stuff, it was quite surprising. The probability is about 1/3, which is not at all near, not anywhere near 100%. Now, let's look at this again. These figures seem to indicate that the test is quite reliable. This seems to be a good enough chance to detect the disease if it's present, and this doesn't seem a big problem. The 4% of false positive results doesn't seem a big problem, but actually, this is the answer. If a person gets a positive test, it's not at all certain that he or she has the disease. Okay, this is quite. By the way, this is quite a problem in practical medicine. It's a big issue. All right, let's comment on this. First, how can we explain how is it possible that we get this low probability? Look at this. Look at this from the mathematical point of view. A certain numerator is divided by this same term, it's repeated here, and some other term. So basically, this number reflects the proportion that this term makes in the sum of the same term and something else. So it's about the comparative size of this term and that term. Okay? Now here, a very high probability of detecting a disease, the disease when it's present, is multiplied by the very low probability of its presence. And in this other term, the low probability of obtaining a false positive result is multiplied by a relatively high probability of the absence of the disease. So we have this opposite effects, and put together they produce this paradoxical answer. Okay? Now, some more comments are necessary here. This formula should be treated with caution. There is an assumption that we make here that is not at all obvious, and actually in many cases it's not true. Look at this. P of D and P of D bar. Probability that the person that takes the test has the disease. Where do we get it? We take it from the general statistics that relates to the population as a whole. Okay? Is it really justified? Is it a good idea to substitute this for the probability that the person who takes the test has the disease? Well, it depends, actually. Now, if you choose a person at random, one person from this entire population, if you choose it at random, then of course you substitute this number here and this number here. But actually, in practice, it's not at all typical that people that take a test are chosen at random. Much more typical is the case when a person comes to the medical facility and takes a test because he or she has reasons to suspect that they have a disease. Do you understand this? There might be some symptoms, not decisive kind of symptoms, but some symptoms. And if there are some symptoms, then this probability is absolutely not what we need to use. It's absolutely false. So it only works if we select a person at random. This is point one. And point two is this. Of course, no reasonable person will be satisfied with this result. How can we improve it? Any suggestions? Well, I honestly wish that none of you find themselves in a situation like this, but suppose you do. Suppose it's you who take a test and get a positive result that seem to indicate that you have some serious disease. But because you have taken as probability course, you know that it's not to be trusted. The probability is, that you actually have the disease is relatively low. But how can you take a step forward? How can you improve this answer? Yes, you can take the test again. Yes, that's right. This is a good idea, but we must make this reservation. Yes, the advice is to take the test again, but you must do everything possible to make this test, the second test, independent of the first one. So it would be a good idea to go to a different medical institution and maybe use a different method of testing, if it's possible, or different apparatus, whatever. So if you do it at the same place with the same nurse, there is a very big chance that there will be the same mistake made the second time. Okay, well, I think I can just write this formula for repeated testing. Or maybe, okay, maybe this is something that you can do at home. Let me use this remaining time to introduce another problem like this, because Bayes' rule is such an exciting thing. It can be applied in many very interesting situations. Example. Well, some individual, let's call him Smith, is suspected of committing a crime. Okay? Well, he's a suspect in a crime. And the police detective who investigates the case considers that there is a 50% chance that Smith actually committed the crime. So there is this 50% chance. Okay? But then something interesting appears as evidence. Now, evidence is obtained that the actual criminal, the person who actually committed the crime, is left-handed. So this is additional evidence. Additional evidence. Well, in police terminology, it's called perpetrator, the person who committed perpetrator. Okay, perpetrator is left-handed. This is some additional evidence. Is left-handed, and Smith is left-handed. Smith is left-handed. Well, what do you think? Does it improve the chances that he is the guilty person? Well, yes, because there is a relatively small proportion of left-handed people in the entire population. Actually, I just consulted the Wikipedia, and if we believe the Wikipedia, about 15% of the total population are left-handed. So 15% are left-handed. Okay. Now, let me add some terminology here. This is called prior probability. This is the probability that we have at the beginning of this story, okay? Before we receive this additional piece of information. It's called prior. But then we receive this additional piece of information, the information that the actual criminal is left-handed. And we establish that Smith is also left-handed, which gives us reasons to revise the probability. And the probability that we compute using the Bayes formula is called revised probability. Okay? Now, what's your guess? What is the revised probability here? You have all the information that is relevant before your eyes here. More than 50%. Well, but by the way, it's the correct answer. It's the revised probability is going to be higher than 50%. Why is that? Why do you think so? It's higher because there is a comparatively small proportion of left-handed people in the total population. If this were 80%, it would be the other way around, okay? All right, please do it, try doing this at home. Thank you, see you next time.